All right, let's click that out of the way. Sorry about my computer deciding it needed a reboot. So last time we were looking at the limit of sine x over x, and we were seeing a discrepancy in the calculator for whether we were in degrees or radians. But basically, the closer and closer you get to 0, it turns out this graph actually approaches 1. So this is going to be one of our special trig limits that equals 1. But we'll play around with that more later. This is a different graph that the more and more you zoom in, the wackier and wackier the values get. But that's because 1 over x, as you get closer and closer to 0, becomes increasingly large, and sine just alternates between 0 and 1. So as the values get increasingly large, sine alternates back and forth between -1 and 1 faster and faster and faster. So this is a very ridiculous thing that we would not ask you the limit of, but graphically it's a very wacky, like the limit absolutely does not exist. So overall, we saw a function's limit exists if and only if its left and right-sided limits are the same. We've seen that limits can be infinity. We've seen that limits sometimes don't exist. But very often the idea of a limit is as we get closer and closer to an x value, the y values are getting closer and closer to a particular value as well. And for most graphs, it's whatever the actual function value is at that point. But this entire definition doesn't require there to be a value at the point. The whole point of this definition is as we get really close to that value, whether we can attain that particular value or not, as long as the two sides are coming in and getting closer and closer to the same value, we say the limit exists. So now that we've got that idea of a limit zooming in, we're going to start looking at how do limits apply to more peculiar situations. So here we've got two functions. F of x equals x plus 4, so it's a diagonal line. And then g of x equals sine x plus 2, which is just an alternating back and forth curve. And when we add them together, we get a line that kind of alternates, but it's also increasing now. So we can see when we add the two functions, like we're just adding the y values, right? So same kind of thing applies to limits. So we have this giant text box of doom from the book. But the too long didn't read is we can add, subtract, divide, multiply, and even take powers and roots of limits. So like in here, the quotient law for limits, the limit of f of x over g of x is the same as the limit of f of x divided by the limit of g of x. And then if we know what those limits are, in this case, they're predefined to be L and M, then we just divide the two, L divided by M, assuming M is not 0. Constant multiple law, if there is a constant number being multiplied to some function, then we can pull the constant outside the limit and just do the limit of f of x, which they defined to be L, so we get a result of the constant times the number L. And the root law is like the only qualification on it is if you're doing an even root, like a square root, just make sure the inside's not negative and it's fine. So that means we can evaluate wacky looking things like this. So the limit as x approaches 7 of f of x times h of x divided by g of x. So what we can do with this limit is essentially the limit distributes across multiplication and division. Like that's what the previous long block just told us, is that I can split this so it's the limit of the top of the fraction divided by the limit of the bottom of the fraction. Bottom of the fraction was g of x. The top of the fraction is still a little complicated. It's f of x times h of x. But another one of our limit laws told us that we can distribute the limit across multiplication as well. So this becomes the limit as x approaches 7 of f of x times the limit as x approaches 7 of h of x, all divided by the limit as x approaches 7 of g of x. And now each of these pieces, I'm going to fill in what I know them to be. So up here, they told me the limit of f of x as x approaches 7 is 11. So this whole entire thing here, I'm going to replace it with 11. Then over here, our limit of h of x as x approaches 7 is equal to 10. So this whole thing for h of x, I'm going to write a 10. And then on the bottom, we have the g of x. So that whole entire bottom piece, I'm going to write 3. So we get 110 thirds, which doesn't divide nicely. So we just leave it as 110 thirds. So same idea for this second thing. We can just push the limit inside multiplication, inside division, inside exponents, inside addition. So instead of writing it all out a step at a time, I'm just going to move that limit in as far as it can. So we're going to have the 7 times, we can move the limit inside that squared as well. Plus 6 times the limit as x approaches 7 of g of x plus 2. The limit as x approaches 7 of 2 is 2. Then we can just fill in the pieces. So this guy is 11 and g of x is 3. So now I'm just going to recopy the other pieces. So this is 7 times 11 squared plus 6 times 3 plus 2 equals some horrible number. And this is why we have calculators. $867. Now, we're not often going to see problems where they're giving us just arbitrary functions. Usually we're going to get like full polynomials, trig functions, like whatever they want in there. The point is, though, this limit goes into all of those operations, goes into all the polynomial functions fine. The trig functions get a little weirder. So now I've got two different weird looking graphs. And then my question is the limit as x approaches 3 from the right, because it's got the little plus afterwards. So of f of x plus g of x. All right, so I can write this so I have the limit on each piece. And now we're just going to figure out, well, what is the limit of f of x as we approach 3 from the right? All right, so here's my 3. From the right means from this side. So now we want to look at what the function's doing. And the function values from the right are starting way up here and getting closer and closer to what's our function value? Our y value for this location. Yep. All right, so this guy is 1. Even though the circle is not filled in, that's what the values on the right are coming towards. Now, same thing for g of x. As the x values get closer and closer from the right, our graph is coming up to this location. And that is a function value of 2. So the limit split across addition. We found the limit from each graph as we approached from the right only. So even though on f of x, the limit as x approaches 3 overall doesn't exist because the left and the right side are not agreeing, this limit only focused on the right side, so we could still evaluate it. We could still work out an answer. So all those limit laws, all the examples were written in terms of functions, just random f of x's and g of x's. We want to break this down and think of like what are the simplest functions you can think of from algebra class, like the simplest, boringest graphs. So a line mx plus b. Now, can we make mx plus b like even more basic? Like what's the most basic line we can think of? Yep. And then what about making the slope even more boring? Yep. And then the flip side of that is, well, what if we didn't even have an x? So y equals x is the perfect diagonal line. Our input is the same as our output. So it's one of the most basic functions because what you see is what you get. Then y equals b, whatever value that is. That graph is just a horizontal line. For any input, the output is whatever constant you're looking at. So those are two of our most basic boring functions. And it turns out the limit of those two guys are very boring. So the limit of x as x is approaching a is just a. As x gets closer and closer to, say, 17, x is getting closer and closer to 17, so the limit's 17. So when we have a constant like that 2 we had before, the limit as x approaches 2, or 17 of the constant 2 would just be 2. So the limit of a number is the number itself. The limit of x is whatever the limit is approaching. So when we come down here and look at this crazy function, let me zoom it in a little more. So this means I can, like we did earlier with the functions, I can distribute that limit through across the addition and subtraction, inside the multiplication, inside the exponents. And I can do that one step at a time, but then it takes forever. So I distributed the limit across all the terms up top, so across the addition and subtraction. And then for each term, I moved it inside close to the x, because I can move the limit inside constant multiplication. I can move it inside exponents. Now for each of these, the limit as x approaches 2 of x, what does that equal? So as we get closer and closer to 2, the limit as x approaches 2 of x. So as x gets closer and closer to 2, what is x getting closer and closer to? 2. So it sounds like a silly question because it is silly. The limit as x is getting closer and closer to 2, and then the function we're asking it about is just x again. So it's like, well, you said we were getting closer to 2, so pretty sure it's 2. So that means inside, for all of our ones with an x, I can fill in that 2. Now the other two pieces are the limit of a constant. So the limit as x is getting closer and closer to 2 of the constant function 1. Well, whatever input we have, we always get a 1 as an output. So that is just the constant number itself. On the bottom, the limit as x approaches 2 of the number 4 is just 4. It's constant. So now kind of look at the result I have here before we do the calculation. And look at the original function we had. So I took my x value of 2 and I just plugged it in for x everywhere. And that's the result we got. So when we're looking at a lot of limits, direct substitution is your first go-to way to do it. And what does this give us? 8 minus 6 is 2, 3 over 12, so 1/4. So especially when the top and the bottom are just polynomials, just the normal kind of functions we spend a lot of time before pre-calculus studying, we just plug in the numbers, we're good to go. So looking at our wacky piecewise limit here. So this one is asking the annoying question, the limit as x approaches 4 of this function. But when we look at the piecewise stuff, well, on one side of 4, it does one thing, and on the other side of 4, it does a different thing. And then at 4 itself, we're just told it's 4. But in order to evaluate a limit, we need to know, as we come from the left, what it's doing on the left side has to match what it's doing on the right side. So anytime we're asked just overall, what's this limit, we have to consider both sides. So we're going to break this guy up to the limit as x approaches 4 from the left, and the limit as x approaches 4 from the right. So part of the writing assignment that I'm assigning to y'all today is understanding how to go between the word description and this notation. So that way, when you write the notation, I want you guys, like, when you're writing it, to like say what the words means. So the limit as x approaches 4, and then the little minus sign from the negative infinity, that's the left side. So now when we look at this function up here, when x is to the left of 4, like which direction is that? So left side of 4, is that the number smaller than 4 or bigger than 4? Yep. Now, when we're looking at our inequalities here, which of these inequalities is going to be the left side? Yep. So that means inside our limit, when we say this limit of f of x on the left, we can substitute in the piece of the function that we know it applies to, which is the 3x minus 4. Now we're just looking at a polynomial. We can directly substitute the 4 in there. So this will be 3 times 4 minus 4. 12 minus 4 is 8. So my limit as x approaches 4 from the left of f of x equals 8. Now we're going to think through the same thing for the right side. So if the left is smaller, the right side better be the numbers bigger, which is our greater than symbol, which is the bottom part of the piecewise function. So 5/9 times 4 to the third power minus 4. All right. I don't know what this is, but I know it's not pretty. It's 284 ninths. Yeah. All right, so I figured out my left side, I figured out my right side. I still haven't answered the actual question here. What's the limit as x approaches 4 overall of this function? Overall. Now, why are you saying that? Yep. So whenever you reach this question of, all right, so which one's the answer? That in itself should tell you something. Like there's no way to choose one of these sides over the other. They're both telling us information that's correct, but they're disagreeing with each other. So that means overall, we can't choose one over the other. So this limit does not exist because the left and the right aren't the same. So this is like the does not equal sign and equal with a line through it. So that's a whole lot of work for no answer. But that is exactly the kind of work that you guys are going to have to do on the test. Like this is one of the first kind of questions, not a piecewise function, but we give you a graph with a whole bunch of different pieces on it. And then we ask you to tell us about limits at particular values on that graph. Like that's what the writing assignment I'm giving y'all today looks like. 2.3 though, the big focus in 2.3 is learning how to do some of the really crazy, stupid algebraic limits. There's like different tips and tricks we can utilize. So the absolute value function, it turns out, can actually be written as a piecewise function. So when the input is greater than or equal to 0, we get x. When the input is less than 0, we do the opposite of that. So this is like, in our head, we know this is what absolute value means. It means strip away the negative. But if we're going to write it more formally as a function, this is the other way that formula comes up, the piecewise definition of it. And that's what we're going to have to utilize in this stupid example here that happens to have an absolute value in it. I say stupid because we don't actually look at absolute values that much in math, but in real world, like absolute value is the measurement metric. Like when you want to know what's the distance from A to B, if you have their like locations on a number line or measurements to them, you typically subtract the two. But when you're saying what's the distance, that's a positive number. But when A and B are arbitrary, you don't know which one's bigger. So you say do the difference and then just make sure you give me the positive number. So like absolute value itself does have a lot of purpose and can actually show up in applied situations a lot. But a lot of times in a lot of classes, we just kind of hand wave the whole like, yeah, it just makes it positive. So this is the like formal mathematical way. And coincidentally, like if you were going to program it on a computer, like this is what's going on behind the scenes with the computer. You end up with cases. So evaluating the limit here. So I'm going to break that limit across all three of these functions. So I've got the limit as x approaches -5 from the left of the square root times the limit on top So for the first two pieces, we can just directly substitute the -5 in there. For this last piece, though, the side that we're approaching -5 is important here. So if I just directly put in -5, I actually get -5 plus 5 is 0. And then I'm dividing by 0, and I'm going to have a problem. Right, so this part will just be -5 plus 14 inside the square root times. We're going to leave the top limit alone as well. So I'm actually going to backtrack this so it's the limit of both pieces again. And this is something that happens like when you're playing around with math, like you're looking at it and then you're like, wait, I made that limit go too far, because we actually need to do some weird algebra here. So on the bottom, the left side of the absolute value of a thing is like the same as our absolute value in here. Like this x inside, I could change that out for x plus 5. So the absolute value of the thing is the thing itself if we're on the positive side, or it's the opposite of the thing itself if we're on the negative side. But it would change these numbers. So when we're on the left side of -5, the bottom is going to become the negative of x plus 5. So I got x plus 5 on top, the negative of x plus 5 on the bottom. So numerically, like those two things, as we get closer and closer to -5, like they're going to keep canceling each other out, except the bottom, since we're coming from the negative side, is always going to be negative. So this whole thing here actually evaluates to just a -1. And then the front part is the square root of 9 times -1. So we end up with -3. Now I'm looking at that whole mess like I could have explained that better. Off the top of my head, I'm not sure how I could have done it a little bit better. So overall, when you're looking at these weird algebra limits, like first step is plug in the number, see what happens. If you plug in the number here, you end up with 0 over 0. 0 over 0 is code word for, okay, direct substitution don't work here. You got to do some algebra madness. In this case, we had to play around with the absolute value to realize we're on the negative side, so that's going to give us a negative. And then we can actually cancel out the x plus 5 and the x plus 5. Like that's what we're actually doing here is. But we're keeping the -1. So let's try a slightly more advanced being a relative term here. Let's look at another weird example. And again, truly, first thing to try is always shove the number in there and see what happens. So 2 times 3 minus 6, that's 0. And then on the bottom, -8 times 3 squared plus 38 times 3 minus 42. Dear God, why? -8 times 9 plus 38 times 3 minus 42. What a shock! It's 0. So if I plug a number into a quadratic and get 0, what does it tell me about that number that I plugged in? So this is like going back to college algebra stuff, which if you skipped college algebra, this is like really going back then. So if I plug in a number and it gives me 0, we call that a 0 of the function. But when something is a 0, that also means for polynomials like quadratics, that that's a factor of the function as well. So 2x minus 6, well, both of those numbers are even, right? So I could rewrite that top as 2 times x minus 3. And that's what we proved on top. When I plugged in 3, I got 0. So that means x minus 3 should be a factor of the top. The same is true on the bottom. I plugged in 3 on the bottom and got 0. So the bottom should also have x minus 3 as a factor. Now it turns out the bottom, though, everything is also even. So before I even try to factor x minus 3 out, I'm actually going to factor out a -2 because, God, that's ugly. So now it'll be positive 4x squared minus 17x and plus 21. So with me so far, that's just cleaning up the numbers a bit. Now we're suspecting x minus 3 is a factor, so I'm going to write that down as if it is a factor, because like I proved it should be one. And now I'm just going to figure out like what would the other pieces have to be so that that would FOIL back out. So I've got an x. It's supposed to multiply to 4x squared, so this side better be a 4x. I've got minus 3. It's supposed to multiply to positive 21, so this better be minus 7. So then I'd get, well, there's what I did wrong. 38 divided by 2 is 19. But -3 times 4 is -12x. And -7x, those add to -19x. So this is indeed the factored form here. So in terms of like what this function is, we can't cancel out the x minus 3's technically. Because having those both in there, that produces a hole in the graph. But when we're evaluating the limit, those two things are always approaching the same thing. So inside a limit, I can cancel those common factors out. So I'm just going to rewrite my limit down here now. I'm going to write all that inside. 2 times x minus 3 over negative 2 times x minus 3 times 4x minus 7. So the x minus 3's cancel out. And for the rest, now we can plug in that 3. So 4 times 3 is 12, minus 7 is 5. So we end up with negative 1/5. So the initial direct substitution told us that this graph is undefined at x equals 3. But we did some creative algebra, got rid of the common factor on the top and the bottom, and now we know that it's a hole at x equals 3, and that hole occurs at negative 1/5. So if we looked at like the actual, move that over. Nope, wrong. So as we get really close to 3, both sides of the graph are approaching this negative 1/5 y value. It actually looked more like that. Then we get some bullshit like this. So if I plug in a 9 on the front fraction, 9 minus 9 is 0. 1 divided by 0. Oh, crap. So instead, we're going to have to do some algebra here, because if I plug in a 9 on the other side, I'm going to get the same thing, 2 divided by 0. So it turns out this guy in here at least factors. Into x minus 9 times x minus 7. So that's like writing out what the first step was. The first step is plug in the numbers, see what you get. We got 1 over 0 minus 2 over 0 equals, I have no idea. That could be infinity, that could be 0, that could be a number. Like right now, we don't know. So that means we're going to have to play around with the algebraic fractions here. So I have 1 over x minus 9 minus 2 over x minus 9 times x minus 7. So since these two fractions separate were like, what's going on? We're going to put them together. So the first fraction, like, what do I need to add fractions? Common denominator. So I already have x minus 9 in both fractions on the bottom. One of them has an x minus 7, the other does not. So that's what we're going to do to the front one, is we're going to multiply by what it's missing. But I can't just multiply on the bottom. I can only multiply by a number that doesn't change the size of the fraction. So in this case, a weird form of 1. So that's why we're multiplying the top and the bottom by x minus 7, because x minus 7 divided by x minus 7 is 1. If I multiply by 1, the fraction is the same size. So now I have x minus 7 minus 2, and then the whole thing is x minus 7 and x minus 9. I'm going to move all that left. So on top, x minus 7 minus 2, well, we can just minus the numbers. That becomes x minus 9 on top. And I just so happen to have an x minus 9 on the bottom. So in our pure algebra sense, I'm not supposed to cancel here, but inside a limit, I can. So the x minus 9s go away, cancel out. They leave a 1 on top. And then I can substitute in the 9. So we have just 9 minus 7 on the bottom. That gives us 1/2. So we went from 1 over 0 minus 2 over 0 to 1/2. So I know these examples get pretty gnarly. And then we get this one, which Chris felt needed a mean. Because that is absolutely the craziness this feels sometimes. So this is where those trig identities that we practiced in pre-cal come back in. So we got to remember, what is tangent the same as? Sine over cosine. All right, now before I actually start messing with the trig, this is my math teacher brain already skipping ahead. Technically, we should plug in the 0. So the tangent of 0 is 0 minus the sine of 0 is 0. Why I got to keep being extra, I'm sorry. I'll just do it here. So 0 over 0. So when we got that 0 over 0 before, we did indeed find something that we could factor out and cancel. The same is true here. So now we're going to go ahead. Tangent is the same as sine of x over cosine of x minus sine of x all over sine cubed of x. Now, most people, when they look at this disgusting mess, like, they don't see that we can factor out a sine x on top. They just see that's a little fraction in a big fraction, and I don't like it, which I agree. I don't like it either. So anytime I have a little fraction in a big fraction, I get rid of it right away. The way you get rid of it is by multiplying by whatever the little common denominator is. We only have the one little denominator, so that's the thing we're going to multiply by on the top and the bottom of the big fraction. Now, you don't have to do it this way. You can factor out the sine x on top. You'd have 1 over cosine x minus 1. And then you can try to play from there. But this is another way to make it do. So we end up with sine x minus sine x cosine x all over sine cubed x cosine x. So now we have sine x times 1 minus cosine x when I factor out the common sine x. So sine x over sine cubed x. Well, we can do some cancellation there. One of the sine x's, it cancels out on top. It's going to leave us with 2 of them on the bottom. Now, one of our other weird remembers is sine squared of x. So do y'all remember a trig identity that had sine squared in it? It's like one of the most common trig identities. So 1 minus sine squared x would equal cosine squared. Now, why does 1 minus sine squared equal cosine squared? Like, where do we usually get that from? Like, if I rearrange that, what's sine squared plus cosine squared? Yep. Sine squared plus cosine squared is 1. So sine squared is the same as 1 minus cosine squared. But 1 minus cosine squared is a difference of squares. We can actually write that as 1 minus cosine x times 1 plus cosine x. So that's what we just got on the bottom is sine squared x, and now I'm going to trade it out for that. So the top is that 1 minus cosine x, ha ha ha, which is one of those two factors. So the 1 minus cosine x on top and the 1 minus cosine x on the bottom, both of those cancel. That leaves us with a 1 as a placeholder on top. And now when I plug in 0, the cosine of 0 is 1. So when I still had the 1 minus cosine, 1 minus 1, I was still getting 0 over 0. Now if I plug it in, though, I get 1 over 1 plus the cosine of 0 times the cosine of 0. 1 over 1 plus 1 times 1, which gives us 1/2. How's that for a disgusting trig review? Let me scroll real quick. All right, so there's a thing we would do with square roots called rationalizing. And it's a thing that nowadays is, in general, a useless skill. The calculator can absolutely calculate 1 divided by the square root of 2. So we don't really have a need to be able to change this into the more common form, square root of 2 over 2. I say more common just because that's the way math textbooks will write it. But how did they turn 1 over the square root of 2 into square root of 2 over 2? Like, what do I have to do here to prove that these two things are equal? Yep. We're going to multiply the top and the bottom by the square root of 2. Now, it's totally normal if your first thought was like, well, to get rid of the square root, you square it. Yes, but we didn't have an equation here. We just had the expression and we were trying to show it was equal to something else. So all I can do is multiply by 1 or add 0. So here, our weird form of 1 is square root of 2 over 2. Now on this bottom one, when I've got more than one term on the bottom, it's like, all right, I can't just multiply by the square root of 2. That's not going to fix the bottom because then it'd be 3 square roots of 2 plus 2. Doesn't help. So what we're going to multiply by on this one is what's called the conjugate. So I need the 3 and the square root of 2 in there, but I'm going to change the sign in between them. So it's a minus. And what this actually creates is a FOIL situation. So on top, 1 times the thing is the thing. So we have 3 minus the square root of 2 on top, and that stays. On the bottom, though, 3 times 3 is 9, minus 3 square roots of 2, plus 3 square roots of 2. So it seems like, your way doesn't work that well either. But the minus 3 square roots of 2 and the plus 3 square roots of 2 are going to cancel out. And then the square root of 2 squared at the end is just going to be 2. So we have 3 minus the square root of 2 all over 9 minus 2 is 7. Now for a number, this is a very antiquated process. The calculator will calculate what 1 over 3 plus the square root of 2 is. But what about if we have something like this? So first step is still plug it in. See if we get something stupid. Don't assume automatically it'll be stupid. Like always double check. You don't have to write this step down if you don't want, but for the notes, like I'm writing it down so it's very clear, like this is still my go-to, like start. See what's going on. So that's the square root of 4 minus 2 over 0. Yep, 0 over 0. So anytime I get 0 over 0, that means there should be some way to cancel something in here. Now, as it stands right now, but there is a square root. So anytime we're trying to get rid of a square root, the conjugate is where you want your brain to go. So let me rewrite that guy. Now our conjugate that we multiply by on the top and the bottom is the same thing as what we have on top because that's where our square root is. So we're going to have the square root of x plus 12. We don't ever want to change what the square root is. And then the other part, we want to keep that the same twos. All we want to change is the minus sign in between those two into a plus sign. So we're not changing what's under the square root. We're changing what's outside the square root between the things. So on top, we're going to FOIL that out. But whenever we're multiplying conjugates, you remember how before we had the minus 3 square roots of 2 and the plus 3 square roots of 2 and they canceled out? That always happens with conjugates. The inside and the outside terms always go away. So it means as long as we're remembering that that cancellation will happen, on top, this will just be still with the limit. The square root of x plus 12 squared minus 2 squared. And on the bottom, don't multiply it out. Just write them side by side. Because we're actually trying to get this x plus 8 to cancel. And that's what's going to happen on top. We're going to end up with x plus 8. So x plus 12, square root x plus 12 squared is just x plus 12. So we have x plus 12 and then minus 4. So 12 minus 4 is 8. Now the x plus 8's cancel. We leave a 1 as a placeholder, and now I can actually substitute in. So I have 1 over the square root of negative 8 plus 12 plus 2. It's the square root of 4 plus 2, 2 plus 2, so this is 1/4. So the bulk of these problems, these crazy limits, this is a whole bunch of algebra skills, algebra practice. The calculus step is just plugging in the number and seeing the 0 over 0, realizing we got to do algebra bullshit, and then getting the 1/4. All right. All right, so if we plug in there, we do get 0/0. But looking at that crazy mess, it's like, why? Like, why did we have a limit approaching a fraction? Like, I don't have a good explanation for why the fraction is this ugly. It just, my colleague wrote it. But whenever we have little fractions inside big fractions, we're going to multiply by those little common denominators to clear the fractions. So it can be a bit of a crazy mess on the in-between, but then we'll eventually end up with just one big fraction with no more little fractions. So we need to figure out what is this common denominator that we're going to multiply this bullshit by. So little 1 over x plus 12. And then little over 9. So I want to multiply the top and the bottom by the 9, but I also want to multiply by the x plus 12. So we are going to put both of those. Anytime we have giant fractions, though, there is always implied parentheses around the top and the bottom. So this is a distribution setup. So I'm going to take this whole 9 times x plus 12, multiply it to the weird little fraction, and multiply it to the 9 we have. And then we're going to do the same thing on the bottom. Multiply this to the x, multiply this to the stupid little fraction. So for the first part, like I'd have 9 times x plus 12 divided by x plus 12. So I'm just going to get a 9. The second part, though, we're going to get 81 times x plus 12. Then to that x, it'll be the 9x times x plus 12 plus, now the 9's cancel, so we just get 109 times x plus 12. So we went from little tiny fraction bullshit to it's a little uglier, but now there's no more little fractions. Now this we could actually multiply through. We're going to have a quadratic on the bottom. Whatever the factor is on top will be a factor of the bottom. We'll get some cancellation. We'll get to a final answer. We only have a few minutes left, and I want to make sure that we have time to take a look at the writing assignment. So here in module 1, it says writing assignment for section 2.2. I'm not going to do a writing assignment for each section. Now, if you looked at this like last night or before class, it was like, this is not opening until 10:30, because I just picked an arbitrary time while we were in class. But there is a docx and a PDF file here. So I'm going to open the PDF in a new tab, but the submitting here is going to be a file upload. That's going to be a PDF. You get 3 attempts just in case you screw up the upload once or twice. If you need more than that, email me. I can help you figure it out. The due date, though, is today at 11:59. So at some point today, you don't have to print this. You can write your answers on a piece of paper and just turn in that submission. But we have a very crazy looking graph. And then we have 5 questions. I should have numbered them. I apologize for not numbering them. Feel free to just number them 1, 2, 3, 4, 5. But notice it's all words. What is the limit of f of x as x approaches 2 from the left? So I'm not just looking for, it approaches 7. It doesn't approach 7. 7's not even on the picture. But I also want you to practice writing the notation. So translate what is limit of f of x as x approaches 2 from the left. How do you write that in math notation? And then equals whatever number you say is that answer. So there's not a lot of writing here, but there's a fair amount of thinking. Y'all can work together, but everyone has to submit their own file. You do need to do it with handwriting. So even if you are a computer programming whiz and you're comfortable typing math, I still want you to handwrite it because you're going to have to handwrite it on the test. To be honest, it takes more effort to type this shit than it does to write it. Because typing in math is a giant pain. So, like you can see, this graph has a lot of weird stuff going on, but this is very similar to the first question we put on the Cal 1 test. Like it's a crazy graph like this, and then we ask y'all a whole bunch of questions about limits at different values. Now on the test, we ask a little bit more, but we haven't gone into that more part yet where we talk about the types of discontinuities because we haven't even talked about continuity yet. But that's that one. So do y'all have any questions before you run away to your next class? Like on what I'm looking for here, turning it in as a PDF. Now, if you want to digitally print this and like write on it on the screen, that's fine. Or if you want to print it out and write on it by hand, that's fine. Like it's not bad practice to have this to put in your notebook just as an extra like reference tool. Because like I said, this is really similar to the first question we typically put on exam 1. All right. Well, email me or hit me up on GroupMe if you're like, I don't know what she's asking here. Or make sure you're working on the web work as well. Some of those questions, like the last one in 2.2 has like 20 parts or something stupid.